Hi everybody. In this video we are going to learn about the repeated measures ANOVA, which is the test we use when we measure the same group of people 3 or more times and we want to compare those measurements against each other. In last week's class we talked all about the between groups ANOVA, which is the test that we use when we have 3 or more separate groups of people that we want to compare against each other. This week we'll focus on the repeated measures ANOVA, where we have the same group of people who we're measuring 3 or more separate times. As we talked about last week, the between groups ANOVA is an extension of the independent t-test. The independent t-test allows us to compare 2 separate groups of people, but as soon as we add a third group, or a fourth, or a fifth, we have to use the between groups ANOVA to compare those 3 or more separate groups. In the same way, the test that we're covering today, the repeated measures ANOVA, is an extension of the dependent t-test. If we measure the same group of people twice, and we want to see if their scores changed, we would use a dependent t-test. However, if we measure the same group of people 3, 4, 5, or 8 times, we would use a repeated measures ANOVA to see whether those people's scores changed over time. Before we see how to do this test in SPSS, I'll explain a few brief examples of situations where this test might be used. In one study, for example, the researchers wanted to test the beneficial effects of vacation on employees' well-being. So they recruited a sample of 131 teachers and had them complete questionnaires about their burnout at 4 different points in time to see how taking a vacation affected the level of burnout that they experienced. The graph at the bottom right shows their results, as does the table at the top. As you can see, each participant in this study was measured 4 times. Time 1 was immediately before they went on vacation. Time 2 was as soon as they got back from vacation. Time 3 was 2 weeks after they got back from vacation. And time 4 was 4 weeks after they got back from vacation. As you can see in the graph on the bottom right, people's level of exhaustion was much higher before they left for vacation than it was right after they got back at time 2, which would suggest that taking a vacation was actually beneficial. Then, as they kept working after they got back, the benefits of vacation slowly went away, as evidenced by the fact that their level of emotional exhaustion went up at time 3 and then back up again at time 4, to the point where at time 4, people's level of emotional exhaustion was no different compared to what it was before they went on vacation. By making these comparisons, the authors concluded that going on vacation did have a beneficial effect. It did decrease the amount of burnout that people were feeling. However, the benefits of going on vacation faded away within a month. In other words, after people had been back from their vacation for a month, their level of burnout was back up to where it was before they left. Here's a new study that looks at how different methods of administering psychological tests might produce different results, and in some cases, more informative results. The news headline here read, "Robots may be better at spotting mental well-being issues in children than traditional methods." In this study, the researchers wanted to measure children's mental health. And what they did is they had each child measured their mental health 3 different times in 3 different ways using the same scale. First, each kid in this study completed a self-report survey which was administered by an adult researcher. In addition, the child's parents completed the same survey on their behalf in which they reported their sense of their child's own mental health symptoms. Third, in another session, each of these children was administered the same self-report survey that they had previously completed, but now, instead of it being administered by an adult, it was administered by a robot, like the one pictured in this photo. Now, even though each of these kids was measured 3 times and administered the same scale just in different ways, what the researchers found was that the way that they received the scale dramatically affected their scores on that scale. Specifically, compared to when they completed the survey with an adult, or compared to when their parents completed the survey for them, when kids completed the same survey in the presence of a robot, they actually produced higher scores on that same scale, which the researchers interpreted as evidence that the kids were more comfortable disclosing their mental health issues and symptoms to a robot than they were disclosing those things to an adult. As you can imagine, that finding might have some obvious, interesting implications for how we obtain mental health data from children. As a reminder from last week, ANOVA is a two-step process because it's an omnibus test. By omnibus test, we mean that we're comparing 3 or more means against each other. But instead of comparing them 2 at a time, the ANOVA test compares all of them against each other at once, which serves to keep the error rate low. Our null hypothesis for an ANOVA is always going to say that these means, whether there's 3, 4, or 12 of them, are all equal to each other. In other words, none of the means is different from any of the other means. Step 1 of the two-step process is going to be to test for what's called a main effect. We're trying to see if any of the means are different from each other. We will determine whether there's a main effect by using an F-test. If the results of the F-test show that there is a main effect, what that tells us is that at least 2 of these means are different from each other. But it doesn't tell us which means are different and which means are not. In order to answer that question, we then have to perform a second step called post hoc tests in order to determine which means are different and which means are not different. However, if the result of our F-test in step 1 indicates that there is not a main effect, that tells us that all of the groups or all of the means are in fact equal to each other. In that case, there's no reason for us to perform post hoc tests because we already know that none of the groups are different. The first example we'll look at today looks at the phenomenon of order effects. Order effects basically means that when we receive a bunch of information in a given order, we tend to be more strongly influenced by information that appears at the beginning of the list, aka primacy effects, and by information that appears at the end of the list, aka recency effects, compared to information that's hidden in the middle of the list. In memory research, for example, if I asked you to memorize a list of 50 words, your memory for the first 10 words and the last 10 words would be better than your memory for the 30 words that appeared in the middle of the list. The study that we're going to use for our first example asks the question, can order effects also influence people's preferences for different things? In this study, the researchers analyzed real-world data from whiskey tastings, where each participant tasted the same 4 whiskeys in a random order, and they rated each of those whiskeys on a 1 to 10 scale, where higher numbers indicated that they liked it more. Now, the researchers in this study weren't interested in the specific whiskeys themselves. What they were interested in was to see whether the order mattered. In other words, regardless of which whiskey people drank first or last, did people tend to like the first whiskey and the last whiskey better than the whiskeys that they tasted in the middle? As I mentioned a minute ago, for an ANOVA, our null hypothesis always says that none of the means are different from each other. So in this case, our null hypothesis would say that people's ratings of the 4 whiskeys will be all equal to each other. They'll like the first one, the second one, the third one, and the fourth one all equally the same, such that order will have no effect on their ratings. The data file for this example is called whiskey.sav. If you want to pull that data file up now, you can go ahead and pause the video right now. To run a repeated measures ANOVA, we're going to go back into the Analyze menu where we were last week, and we're again going to select General Linear Model. However, last week we selected Univariate to run a Between Groups ANOVA. This week we'll select Repeated Measures to run a Repeated Measures ANOVA, which will allow us to compare people's ratings of these 4 whiskeys against each other to see if order had any effect on their ratings. When we click on repeated measures, we see something that we haven't seen before. This is the menu that pops up. In this menu, we need to do two things. First, we need to give a name to our independent variable. Here, I chose to call it order, but it really doesn't matter what we choose to call it as long as it's something that we remember. Whatever we choose to call this variable, we're going to type that word in the box where it says within subject factor name. More importantly, we have to tell SPSS how many levels there are of our independent variable, or in other words, how many measurements each person provided, how many times each person was measured in our study. In this study, each participant tasted and rated 4 different whiskeys. Therefore, we have 4 levels of our independent variable, the first, second, third, and fourth ratings that each person gave. So where it says number of levels, we're going to type in the number 4, and then we're going to click add, at which point our variable name and the number of levels will appear in the box next to the add button. Once we see that that variable name and number has appeared in that box, we'll be able to click the define button at the bottom of this window to move to the next screen. When we click define, the window that we'll see will look something like this. On the left, in the box that's now empty, what you should see is a list of all of the variables that we have in our data file. In this file, there are only 4 variables: people's ratings of the first whiskey, the second whiskey, the third whiskey, and the fourth whiskey that they tasted. What you'll initially see on the right-hand side are 4 question marks. That's SPSS's way of telling us we need to know which 4 variables correspond to the 4 measurements that each person provided in this study. So all we need to do is select the 4 whiskey variables and move them over from the left-hand box to the right-hand box, at which point they'll replace the 4 question marks. This is our way of letting SPSS know each participant in this study was measured 4 times, and these variables correspond to the 4 ratings that they gave. Before we click OK, there's 2 other things that we need to do. First, in the options menu, identical to what we did last week, we're going to select the options for descriptive statistics and effect size. This will give us the mean and standard deviation for each of the 4 measurements. So, for example, on average, how much did people like the first whiskey, the second whiskey, and so on. And it will also give us an effect size, namely eta squared, for our f-test, which will allow us to make an inference about how strong the effect was. The other thing we need to do is request post hoc tests in the event that we do find a main effect, and we need to figure out which of these ratings were different from which others. When we ran the Between Groups ANOVA last week, we clicked on the post hoc menu, which gave us 18 different options of post hoc tests that we could perform, and what we ultimately chose was to use the Tukey post hoc tests because it's neither too liberal nor too conservative. For the repeated measures ANOVA, however, we are going to select the EM means option to request post hoc tests. When we click on EM means, on the left side of the window, we will see a list of all of our independent variables. In this case, we only have one independent variable, which I previously gave the name order to. So we're going to select that variable on the left and hit the arrow button in the middle to move that independent variable over to the box on the right, where you can see it here highlighted in yellow. The other thing we'll need to do is check the box next to where it says Compare Main Effects. This is where we're asked for post hoc tests. To choose which post hoc test we perform, we use the drop-down menu under Confidence Interval Adjustment. Now you'll see here that we have far fewer options for post hoc tests this week than we did last week, and Tukey is not one of those options. So since we can't use Tukey, we will select Bonferroni as our post hoc test for the repeated measures ANOVA. So select Bonferroni from the drop-down menu, click the Continue button, and then back on the main window, we can now click OK to run the test. When the output window appears, you'll notice that this test produces a lot of output, a lot of which we don't even need. So what I'll do now is focus you in on the parts that actually matter. In order to look for the main effect, we're going to look at the table called Tests of Within Subjects Effects. We're going to use the row that's labeled Sphericity Assumed. Sphericity is an assumption similar to homogeneity of variance, which we talked about in previous weeks. And for our purposes, we're going to assume that that assumption has been met and use the output from the sphericity assumed rows in this table. This table gives us the results of our f-test that will tell us whether we have or have not found a main effect. In this case, our f statistic for our independent variable order is equal to 42.768, which will round to 42.77. As we saw last week, ANOVA requires not 1 but 2 degrees of freedom values. In this case, those values are 3 and 393. So when we write up our answer, we'll include both of those degrees of freedom values in parentheses next to the letter F. The most important number here, of course, is going to be our p-value, which in this case is very small, less than 0.001, which tells us that we did in fact find a main effect. So what we know at this point is that when people tasted 4 whiskeys, they did not rate all 4 whiskeys as the same, as equally good. Instead, it appears that order did have some effect on their ratings. But we don't yet know which whiskeys people tended to rate more favorably than others. We can also look at the effect size here, partial eta squared, equal to 0.25, which indicates a strong effect using the guidelines that we talked about last week. So now that we know that people did not in fact rate all 4 whiskeys the same, we will need to look at the results of the post hoc tests to determine which whiskeys they liked better than others. The table called Pairwise Comparisons shows us the results of our Bonferroni post hoc tests. And you'll notice it's structured very similarly to the multiple comparisons table that we used last week to interpret the results of the Tukey post hoc tests. Now, the first thing we'll need to know about this table is what these numbers on the left-hand side mean. The first row, for example, tells us that Whiskey 1 and Whiskey 2 were significantly different from each other. As we saw last week, we'll start with the number on the left, which tells us that we're comparing our first whiskey against our second whiskey. The p-value of 0.001 tells us that there is a significant difference here. And the fact that the mean difference is positive, in this case positive 0.372, tells us that on average, people rated the first whiskey as tasting significantly better than whichever whiskey they drank second. The one thing that's confusing about this output is it doesn't show us the verbal labels that correspond to each of the 4 measurements. Now in this case, it just so happens that 1 corresponds to the first whiskey, 2 corresponds to the second whiskey, and so on. But if these groups weren't in that order, we could use the table at the very top of our output, the table labeled Within Subjects Factors, as sort of a key to understand which of these comparisons corresponds to which of these groups. So in the table, for example, we see that 1, which means people's rating of whiskey number 1, is being compared against 2, which is people's rating of whiskey number 2. We can refer back to this table as needed when we're performing the rest of the comparisons. So far we know that the first row of output in this table tells us that people rated whiskey number 1 as tasting better than whiskey number 2. What we now need to do is perform the rest of these comparisons. And as you can see here, there's a total of 6 comparisons that we need to perform. 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. The easiest way to do this, in my opinion, is to first see if there are any whiskeys in the table, or any means that is, that are significantly different from all of the others. For example, if we look at whiskey 2, which in the highlighted portion is being compared against whiskeys 1, 3, and 4, we see that all of those differences are significant, and all of the mean differences are negative. What that tells us is whiskey 2 was rated as less delicious than whiskeys 1, 3, and 4. In other words, out of the 4 whiskeys, whichever whiskey people tasted second was consistently their least favorite. On the other hand, if we look at whiskey 4, which in the green highlighted area is being compared against whiskeys 1, 2, and 3, we see that all of those differences are significant, and all of those differences are positive. What that tells us is people rated whiskey 4 as tasting better than whiskey 1, whiskey 2, and whiskey 3. In other words, whichever whiskey people tasted last was reliably their favorite. The only remaining comparison is a comparison of whiskey 1 against whiskey 3, which we see in the highlighted purple area at the top. The p-value of 0.076 tells us that there was no significant difference in people's ratings of the first whiskey as compared to the third whiskey. Now it's up to us to fit all of this together. We know which whiskey was people's favorite, we know which whiskey was people's least favorite, and we know which whiskeys were not different from each other. Another strategy for making sense of these post hoc test results is to try to visualize the order of the groups in terms of a ranking. Here I've created a little scale that ranges from best to worst. Now, we've already seen in the green highlighted area that whichever whiskey people drank fourth, they liked better than the first, the second, and the third. In other words, whiskey number 4 was always people's favorite. Whiskey number 2 was always people's least favorite. As shown in the red highlighted area, whiskey number 2 was always rated lower than whiskey 1, whiskey 3, and whiskey 4. That leaves us in the middle with whiskeys 1 and 3, which had lower ratings than whiskey 4, higher ratings than whiskey 2, and equal ratings to each other. Using a chart like this before we go about writing our results should enable us to explain the results more clearly. Speaking of the results, here's how we'd write them up for a study like this. As we saw last week, we're always going to start with a single sentence that explains whether we did or did not find a main effect and explains what analysis we did. In this case, since we did find a main effect, that sentence would say, a repeated measures ANOVA revealed a main effect of order on people's ratings of the 4 whiskeys. As always, at the end of the sentence, we'll include our test statistic, which in this case is F, our degrees of freedom, which in this case we have 2 of, our p-value, which was very small, and our effect size, which indicated a large effect. Now that we know there is a main effect, the second part of our write-up will explain which whiskeys were and were not different from each other. We'll start by naming the type of post hoc test that we did, in this case Bonferroni, And then it's our job to try to explain all of the post hoc comparisons that we saw in the previous slide. Here I said post hoc Bonferroni tests indicated that people rated the fourth whiskey as better than the first, second, and third whiskeys. That first sentence establishes that the fourth whiskey was rated as better than all three of the others, and it also includes the means and standard deviations for each of the four whiskeys. Remember that once we report those means once, we don't have to keep reporting them every time we refer to that whiskey again. The second sentence establishes that the second whiskey was people's least favorite. Our post hoc test showed that people rated the second whiskey less favorably than the first and the third. Finally, our last sentence explains that the first whiskey and the third whiskey were rated as equally good. So our conclusion here is that order did have an effect on people's preferences. Regardless of which whiskey they had first or second or third or fourth, people reliably liked the fourth whiskey the best and the second whiskey the least. This is based on a real study published in 2018. In this study, the researchers used real-world data from actual whiskey tastings, but in those tastings, participants actually tasted 7 whiskeys rather than 4. But they would still use a repeated measures ANOVA to compare those ratings because the same people were measured 7 times. As you can see from this graph, they found very similar results, where whichever whiskey was tasted second was people's least favorite, and as they got deeper into the tasting, people tended to prefer whiskeys that were later in the sequence. The second example that we'll walk through today looks at the phenomenon of near misses in gambling. The picture at the top left shows what might be considered an example of a near miss. This person did not win the lottery, but each of the numbers that they picked was only one number off from the numbers that were actually selected. Same thing on the right. If you're playing a slot machine and you get 7-7 cherry, you almost won, but you didn't win. The phenomenon of near misses is important because research with adults has shown that near misses feel different psychologically compared to obvious losses. But in actuality, near misses are still losses. The reason this is important is because a near miss, because it feels almost like a win, can encourage people to keep gambling. The study that we'll use for our second example looked at whether children display this same tendency. In other words, when kids are playing a game and they don't win, but they almost win, does that feel different, qualitatively different, from when they obviously lose? The participants in this study were kids who played a game called Colorama. Some of you might be familiar with this game. You see it in arcades and boardwalks sometimes. Each kid in this study played this game 20 times. Now, for those of you who might be unfamiliar with how this game works, it's quite literally just roulette for kids. There's a wheel in the middle that has different color stripes on it. A ball is released into the wheel where it spins around, and kids place bets on which color the ball is going to land on. Every time they play, they either win, meaning they selected the correct color that the ball landed on. If the ball lands in a color directly next to the color that the child picked, that was counted as a near miss, meaning they almost won, but the ball didn't quite make it into the right spot. And then if the ball lands on a color that's completely on the other side of the wheel, not even touching the color that the child bet on, that's considered a loss. As I mentioned a minute ago, each kid played this game 20 times, with the idea being that they would sometimes win, they would sometimes lose, and they would sometimes have a near miss. After each of those 20 times, each child was shown this 5-point scale and asked to indicate how close they were to winning. I lost means 1, I won is a 5, and if the child felt that they were somewhere in between losing and winning, they could select 2, 3, or 4 in the middle. So by the end of this study, each child who completed this game 20 times should have 3 mean measurements. What was the average rating of the times that they won? What was their average rating of the times that they lost? And what was their average rating for the times that they had a near miss? What we might see here is that children tend to rate wins as very different from losses, which makes sense. The question is, do children perceive near misses, which are losses, as being similar to losses, or as being more similar to wins? Here are the data from this study. As you can see, 20 children participated, and they each have 3 measurements: their average rating of wins, their average rating of near misses, and their average rating of losses. Our null hypothesis here says that kids will rate wins, near misses, and losses as being equally successful. Now that's obviously unlikely to happen because if nothing else, kids will understand that wins and losses are different from each other. What these researchers were really interested in seeing is how children perceive near misses, and whether they perceive near misses as being more similar to wins, more similar to losses, or neither. I want to point out in this data file that child number 7 has no data for wins. That's because this one participant, despite having played the game 20 times, did not win in any of those 20 times. So because this person has missing data for one of those 3 measurements, they will automatically be excluded from the repeated measures ANOVA, so our results will be based on the 19 other kids who do have ratings for each of the 3 outcomes. As a reminder to run this test, we will go to Analyze General Linear Model Repeated Measures, and the first thing we need to do is give our independent variable a name. In this case, I chose to call it outcome because there are 3 possible outcomes to the game. More importantly, we have to indicate how many levels there are, or how many times each child was measured. Because there were 3 possible outcomes, win, near miss, and loss, we're going to enter 3 in the number of levels box, and we'll click Add to add that variable to our factor list. Once we've done that, we'll be able to click Define to advance to the next screen. Here is that screen. As a reminder, at first you will see a list of all of your variables on the left and 3 question marks on the right that correspond to the 3 measurements that we obtained from each child. The first thing we'll do is we'll select those 3 variables and move them into those question mark spots on the right to replace the question marks in the within subjects variables box. This is our way of telling SPSS these are the 3 measurements that we want to compare against each other. In the estimated means menu, we will select outcome from the factor list, click the compare main effects box, and select Bonferroni from the drop-down menu to tell SPSS that we want to perform Bonferroni post hoc comparisons in the event that we do find a main effect. In the options menu, we will ask for descriptive statistics, which will give us means and standard deviations for each of the 3 outcomes, as well as a measure of effect size for our f-test. Here are the first 2 tables of output that we get when we run this test. As we saw a few minutes ago, on the left, we get a key that tells us which of the 3 levels of outcome corresponds to which of the 3 measurements. So in this case, children's ratings of times that they won is considered outcome 1, their ratings of near misses is considered outcome 2, and their ratings of losses is considered outcome 3. Those three outcomes each have a mean rating, which are shown in the table on the right. On the 1 to 5 scale, kids on average rated wins as a 4.96 out of 5. They rated near misses as a 3.31 out of 5. And they rated losses as a 2.83 out of 5. Remember that this 5-point scale is asking kids to rate how close they were to winning, where 1 means a loss and 5 means a win. So these means suggest that kids are in fact discriminating between wins and losses. But then we have near misses where the mean falls somewhere in the middle. When we find the tests of within subjects effects table, this table will tell us the results of our F-test and therefore whether we have or have not found a main effect. As a reminder, we'll use the output in the sphericity assumed rows of this table. The F statistic here is huge, 107.31. Our degrees of freedom values are going to be 2 and 36. Those are all numbers that we're going to want to include in our final answer. Our p-value here is very small, less than 0.001, which tells us that the kids who participated in this study did not rate all three of these outcomes equally. In other words, wins, near misses, and losses were not perceived as identical by these kids. However, we do not yet know which outcomes were rated differently. Our effect size here is very, very strong, an eta squared value of 0.86. Next, we will look at the pairwise comparison table to see the results of our Bonferroni post hoc comparisons. I've also included the within subjects factors key from the top of the output so that we can use that key to understand which groups are being compared against which in the table. The first row compares outcome 1 against outcome 2, or in other words, compares children's ratings of wins against children's ratings of near misses. The p-value tells us that this was a significant difference, and the mean difference tells us that children rated wins as more successful than near misses. The second row of output compares outcome 1, wins, against outcome 3, losses. The p-value here again is significant, and the mean difference again is positive, which tells us that children rated wins as different from losses. So as one might expect, the kids in this study rated wins as being more successful than both near misses and losses. The remaining question is, did kids perceive a difference between losses and near misses, even though both of them really are losses? To answer that question, we find the row of the table that compares outcome 2, near misses, against outcome 3, losses. We again see a significant p-value of 0.007, and we see a positive mean difference, which tells us that on average, kids perceived near misses as more successful than losses. So not unlike adults, kids tend to perceive near misses as more successful than losses, even though in actuality, both are losses. Here's how we might explain these results. First, we'll include our one-sentence explanation of our main effect. A repeated measures ANOVA revealed that children did not perceive all three of the outcomes of the game as the same. There's our F statistic, our degrees of freedoms, our p-value, and our eta squared. As we expected would happen, children were able to discriminate between wins and losses. So one of our Bonferroni tests indicated that children's ratings of wins was significantly higher than their ratings of losses. That's not terribly surprising. Near misses, however, were rated as significantly different from both wins and losses. According to our Bonferroni tests, kids perceived near misses as less successful than wins, but also as more successful than losses. In other words, all three of these outcomes, wins, near misses, and losses, were all perceived as different by the kids in this study. Here's how the authors explained their results in the original paper. They explained that they performed, as we did, a repeated measures analysis of variance to compare kids' mean ratings of each of the three types of outcomes. As we've discussed a few times, the ANOVA is an omnibus test that tests for overall differences, and they describe it as such in the section that's highlighted in green, where they also report their degrees of freedom, their F-statistic, and their p-value. Because this is a somewhat older paper, 2016, they don't report an effect size, but nowadays you'd probably see an effect size there as well. They then performed Bonferroni post-hoc tests to compare the three ratings against each other, and what they found was that kids rated losses and near misses differently, misses and wins differently, and losses and wins differently. Just like we did, all three of those ratings were significantly different, and their conclusion is that the participants in this study perceived near misses as different from wins, but also different from losses. Our next example will give you a little more leeway to practice on your own. This example is based on a study that asked the question, does gardening improve mental health? In this study, participants completed a 4-week gardening class, during which time they completed the BDI, the Beck Depression Inventory, 4 times. The first time they completed the Beck Depression Inventory was before starting the class. This served as the baseline for their level of depression. They then completed the BDI again 2 weeks into the class, or in other words, when they were halfway through taking the class. They then completed it again at the end of the 4-week class, and the final and 4th time they completed the BDI was 2 weeks after they completed the class. This measurement was included to see whether the benefits of gardening continued to persist even after the class had ended. Here's where we are going to run this test. The gardening.sav data file shows us for each participant all 4 of their BDI scores. Before the class, halfway through the class, at the end of the class, and 2 weeks after the class. When we go to Analyze General Linear Model Repeated Measures, we're going to give our independent variable a name. In this case, I chose to call it time. And it has 4 levels that correspond to those 4 times that each participant completed the Beck Depression Inventory. We'll then click Add and click Define, at which point we will move the 4 measurements, BDI pre, 2 weeks, 4 weeks, and post, to replace the 4 question marks in our within subjects variables list. As we've seen a few times now, in the Options menu, we'll select Descriptive Statistics and Effect Size, and in the EM Means menu, we'll select Bonferroni post-hoc tests. Here is our output. First, we have the results of our tests of within subjects effects, which is the F test that tells us whether we've found a main effect or not. Note that I've truncated some of this output so that it would all fit on the slide. We also have our pairwise comparisons table, which shows us the results of the Bonferroni post-hoc tests. As a reminder, we can use the within subjects factors table as a key to remind us which times correspond to which measurements. As you look at this output, try to answer the following questions. First, was there a main effect? And in other words, across the 4 times that participants completed the BDI, were their scores always the same? Or were there differences in their BDI scores between at least 2 of those time points? If there was a main effect, we will look at the pairwise comparisons table to understand when exactly participants' BDI scores changed and how they changed. For example, try to answer the following question. Compared to when they first completed the BDI at the beginning of the study, did participants' BDI scores change after doing 2 weeks of gardening? What about after they did 4 weeks of gardening? Was their initial BDI score different from their BDI score at the end of the gardening class? And if so, how? Did the effects of the gardening class persist? In other words, did participants' BDI scores change between the end of the class and 2 weeks after the class? Pause the video now and try to answer these 4 questions on your own. Now that you've answered those 4 questions, we're ready to write up our results. Using the information on the screen, as well as the descriptive statistics, which you'll need to get from SPSS directly, try to write up the results in APA format. Was there a main effect of gardening on depression? And what did that main effect look like? As you explain your post-hoc tests, be sure to explain when and how people's depression levels changed over time. If you want to practice writing this up, pause the video now. Measured by, sorry about that. As measured by a scale called the PSS, which is the graph shown on the left. The graph shown on the right shows depression scores as measured by the BDI. In both cases, you can see that over time, people's stress and depression levels tended to decrease, regardless of whether they took gardening classes or took art classes. Another thing you can notice from these graphs is that whereas participants completed the BDI 4 times, they completed the PSS scale, which measures stress, 6 times. But again, since we're measuring the same group of people repeatedly, we would still use a repeated measures ANOVA to track the change in stress scores over time. Here's our 4th and final example, which you'll complete entirely on your own, and then I'll show you the answer so you can check your own work. The question behind this study is, does swearing increase pain tolerance? To measure pain tolerance, the participants in this study completed what's called a cold presser task, where they hold their hand in a freezing cold vat of water, and pain tolerance is measured in terms of how long in seconds they're able to keep their hand in the water before having to remove it because it becomes too painful. Each participant did the cold presser task 4 times, and each time they did the task, they were asked to repeat one of 4 words while they were holding their hand in the cold presser tank. Some of them said a popular swear word. Others said an innocuous word, table. On another occasion, they said a word that sounds like the swear word, but is not in fact a real word, namely fouch. And then finally, they repeated a nonsense word, which in this case was twizpipe. So again, just to clarify, each participant did the cold presser task 4 times, and on each occasion, they repeated one of these 4 words while they held their hand in the tank. The goal was to see whether repeating the swear word would increase their pain tolerance. In other words, would they be able to keep their hand in the tank longer when they were saying the swear word as opposed to the other 3? The data file for this example is called twizpipe.sav, and for each participant we have 4 measurements. Each measurement indicates how long they were able to hold their hand in the cold water in seconds for each of the 4 words that they repeated while doing this task 4 times. For practice, run a repeated measures ANOVA on these 4 measurements and write up your results, including a graph of the means, which you can use our Excel file that we saw in class last week to make a graph with 4 bars on it, including error bars and formatting and labels and all that other good stuff. Note that these are the actual data from this study. As we talked about previously, it's becoming more common, for the sake of transparency, for researchers to publish their data online along with the published journal article. So what you're using here are the real the real data behind this published study. Take a moment and run this analysis. Tell me whether there was a main effect. In other words, did the word influence people's pain tolerance? And which words produced higher or lower pain tolerance compared to others, according to the Bonferroni tests. Pause your video now to complete this practice problem, and then I'll show you my answer. Here's how I wrote up the results of this study. A repeated measures ANOVA revealed a main effect of words spoken on pain tolerance. In other words, people showed different levels of pain tolerance depending on what word they were repeating while they completed the cold presser task. Eta squared of 0.17 shows that this was a strong effect. Here's a graph that shows people's average pain tolerance for each of the 4 words and the 4 times they completed the cold presser task. The Bonferroni post hoc comparisons indicated that people's pain tolerance was significantly higher when they said the swear word compared to any of the other 3 words. None of those other 3 words, Fouch, Twizpipe, and Table, were significantly different from each other. In other words, it was the swear word and only the swear word that affected people's pain tolerance, supporting the hypothesis that swearing actually does make us more tolerant to pain.